Hello everyone. Today we continue with liquefaction of gases. Liquefaction of gases and how the gases can be converted in liquids we have discussed. First, what we have to do in liquefaction of gases? First, we have to cool the gas. We have to cool the gas. We have to lower the temperature of gas to the temperature below its critical temperature. Okay, so after getting the critical temperature or below critical temperature, we have to apply pressure on the gas. When we apply pressure on the gas, what happens? The gas converts into liquid. So the gas is converted to liquid on applying pressure on the gas below its critical temperature. Below its critical temperature. So how to define critical temperature? The temperature below which only the gases can be converted into liquids is called critical temperature. Okay, so that point we have to understand critical temperature. So next one, Joule-Thomson effect. We started Joule-Thomson effect. Suppose you take one tube like this. Okay, so in this tube here, it is small hole, small aperture. So from this side, we are blowing air. So blow the air. So blow the air at high pressure. Blow the air at high pressure. So at high pressure, we are blowing what air through this area. Now through this small hole, through this small, very fine hole, what is coming? The gas is coming out like this here. The gas is expanding. The gas is suddenly expanding into what? Low pressure region. It is low pressure region. So the gas, the air is moving from high pressure region to low pressure region through a small hole, through a small aperture. This is called what now here? Expansion of the gas. What is this called? Expansion of gas. So expansion of gas means the work is done by the gas. Expansion of the gas meaning what? When gas is expanding, the gas will do some work. Gas will do some work. Okay, so here so far what now here at high pressure the molecules are close to each other. At high pressure condition, the molecules are close to each other. When we apply high pressure, what happens? Volume becomes less. Then the distance between gas molecules will be less. Now, when suddenly the gas expands into low pressure region, what happens now? The gas molecules will be trying to go away from each other. When gas molecules are going away from each other, the attraction force between the gas molecules should overcome. Okay, so this to overcome these attractive forces, between the gas molecules, the gas will do some work. The gas does some work. Okay, so when it is doing some work, when the gas is doing some work, it will consume some amount of kinetic energy. The kinetic energy of the gas will be consumed to do some work here. Whenever energy is consumed, the temperature becomes low. So low pressure, low temperature will be created here. That means what now here? Lowering of temperature, that is falling of temperature is nothing but cooling. So cooling effect will be caused here. So here which effect is caused now? Cooling effect. So the cooling effect is caused whenever gas expands. Whenever gas expands from high pressure region to low pressure region. Okay, the sudden expansion of the gas from high pressure to low pressure through a small hole will cause what now? Cooling effect. This effect is known as what? Joule-Thomson effect. So once again see this. When a real gas is allowed to expand adiabatically, we discussed yesterday this adiabatical condition, through a porous plug or through a fine hole. Through a fine hole means small hole. Through a fine hole into a region of low pressure. Into low pressure region, when you allow the gas to expand, it is accompanied by cooling. It is associated with the cooling here, except for hydrogen and helium, which get heated up. Which get warmed up means what? Heated up. This point we discussed. And next one, cooling takes place because some work is done to overcome what? The attractive forces, intermolecular attractive forces between the gas molecules. As a result, the internal energy decreases, and so does the temperature. That means the temperature decreases. Falling of temperature is called what now here? Cooling effect. And ideal gases do not show any cooling effect, any heating effect, because there are no attractive forces between the gas molecules in ideal gases. That means the ideal gases do not show Joule-Thomson effect. Okay, up to this we have discussed. Okay. Now, next important area what we have to understand is that during Joule-Thomson effect, during Joule-Thomson effect, during this effect, what happens we have to understand here. So, what is the condition first one here? During Joule-Thomson effect, enthalpy of the system remains constant. Enthalpy of the system remains what more? Constant. So, enthalpy means what here? H, delta H. Delta H means here the final enthalpy minus initial enthalpy. The final enthalpy minus initial enthalpy. Final enthalpy minus initial enthalpy is called what ma? Delta H. That is enthalpy change. So enthalpy change. Enthalpy. First of all, what is enthalpy here? Heat content. Enthalpy means what? The total heat content. The total heat content of the system of the gas is called what now here? Enthalpy. The total heat content of the gas or the total heat content of the system is called what? Enthalpy. So final enthalpy of the system minus initial enthalpy of the system will give a delta H. The enthalpy change of the system remains constant. That means H2 value will be equal to H1 value. Therefore, delta H will be 0. Delta H remains what? 0. That is the condition here. Next. So during Joule-Thomson effect, enthalpy of system remains constant means delta H value becomes 0. Next. Joule-Thomson effect or coefficient mu. The Joule-Thomson effect is associated with one coefficient called Joule-Thomson coefficient, which is given by the letter mu. Mu is equal to dou T by dou P. Dou means what? Very small change. This indicates, the symbol indicates what? DHO dou. Dou indicates very small change. So very small change in T divided by very small change in P. So dt by dP. Okay, where constant enthalpy. Enthalpy is what? Constant. This one H. H indicates what here, ma? Enthalpy. At constant enthalpy, dt, the change in temperature by change in pressure, is equal to what now? Mu. Mu is equal to change in temperature divided by change in pressure at constant enthalpy. Okay. Next, for cooling effect, mu should be positive. Mu is equal to positive for which effect? Cooling effect. That means what now? Delta T will be more, delta P will be more. The change in temperature will be more, change in pressure will be more, change in temperature will be more. That's why it becomes what? Positive. The numerator value should be more than denominator. Then the mu becomes what now? Positive. Because the change in temperature, dou T and dou P, or dt and dP will be what now here? Negative. The ratio will be, means what here? These values will be negative. Okay. So the delta H becomes what now here? Positive. Overall, this numerator value should be more than denominator. Then mu is equal to positive. And for heating effect, mu becomes what? Negative. The Joule-Thomson coefficient will be negative for heating effect. For heating effect, negative. For cooling effect, positive. Cooling effect, positive. Heating effect, negative. That point keep in mind. And because dt is positive here and dP is negative. In this first case, when mu is equal to positive, both will be negative. dt and dP both will be negative, whereas the dt will be positive, dP will be negative. In which case, if heating effect is considered, for the heating effect of gases, Joule-Thomson coefficient mu is equal to negative. Because what? The change in temperature is positive. The final temperature minus initial temperature will be positive. Final temperature minus initial temperature will be positive. Got it, here concept? So dt means change in temperature. Change in temperature. The change in temperature, how to write? Final temperature minus initial temperature. Final temperature minus initial temperature. Now for this delta T to be positive, for this dt to be positive, what should be more here? The T final should be more than T initial. So final temperature is more means heating effect has happened. Okay, so heating has happened here. Final temperature is more than initial temperature means what? The gas was heated. The gas was heated. So whenever final temperature is greater than initial temperature, this difference becomes what? Positive. So dt becomes positive. And dP is what now here? Negative. dP negative meaning what? The change in pressure is negative. That means what now? Final pressure minus initial pressure. If you take this difference will be negative. Final temperature is lesser, initial pressure is more. So final pressure is lesser and initial pressure is more, suppose. Then lesser value minus greater value will become what? Negative. So dP will be negative in this case. For what? Heating effect. And here in this case, dt will be negative, dP also will be negative. For mu is equal to positive value. And if mu is equal to negative, that is called heating effect. For this heating effect, delta T will be positive, whereas dP will be, delta P will be negative. Okay, ma? Next, for no heating or cooling, mu is equal to 0. Mu is equal to 0 for no heating and no cooling effect. Because dt will become what? 0. dt becomes 0 here. Now dt when it is 0, 0 by delta P, 0 by dP will be what? 0. So mu becomes 0, in which case when there is no heating effect by the gas or no cooling effect exhibited by the gas. When gas is not showing any heating effect or cooling effect, Joule-Thomson coefficient will be 0. Why it is so? dt will be 0. Okay. So this point mainly you have to understand. So it's about what now? Heating effect and cooling effect. Now tell me, for in which case heating and no cooling, no heating will be there? No heating, no cooling will be there for which gases? For ideal gas. For ideal gases, for ideal gas, no heating effect and no cooling effect. When ideal gas is expanded suddenly from high pressure to low pressure through small hole, it does not show heating effect or cooling effect. That's why for ideal gases, Joule-Thomson coefficient mu is equal to 0. So that point we have to understand. Is that clear, ma? If you want, you take the screenshot of this. Whenever you need any important area in his screen, you take the screenshot immediately, any slide. Okay. Yeah. Next one. So inversion temperature. Inversion temperature. It is also important concept. So inversion temperature is given by Ti. Ti. So it is the temperature. Inversion temperature is the temperature at which gas shows neither cooling effect nor heating effect. So the gas shows neither cooling effect nor heating effect. That is, Joule-Thomson coefficient mu is equal to 0. Exactly at inversion temperature. When you take the inversion temperature of a gas, at that inversion temperature, the gas neither shows cooling effect nor heating effect, and Joule-Thomson coefficient will be 0 because dt will be 0. Because dt, the change in temperature is 0. That's why mu also will be 0. And below this temperature means what? Below inversion temperature. Below inversion temperature, below this inversion temperature of the gas, it shows cooling effect. It means what here? Gas shows what? Cooling effect. The gas will be showing cooling effect below the inversion temperature of that particular gas. So all the gases will not have same inversion temperature. Different gases have different inversion temperature. Okay, at the inversion temperature of a particular gas, that gas will be showing neither cooling nor heating. But below that inversion temperature, that gas will be showing what? Cooling effect. And above this temperature, that means what? Above inversion temperature. Above inversion temperature, the gas will be showing what? The gas will be showing heating effect. Gas shows heating effect above the inversion temperature, and gas will be showing cooling effect below the inversion temperature. Now we can also define inversion temperature in another way. The temperature of a real gas, below which when it is expanded suddenly shows what? Cooling effect. And above the inversion temperature, when gas is expanded suddenly, it will show heating effect. So this is what your inversion temperature. So this inversion temperature is equal to what now? Inversion temperature is equal to HA by 27 RB. HA by 27 RB. So inversion temperature is given by the formula HA by 27 RB. how inversion temperature and A value related directly proportional. Okay. Next, any gas like H2 and helium whose inversion temperature is low, would show heating effect. They will be showing what? Heating effect only. They will not show cooling effect at room temperature. Room temperature means generally what we take 25 degrees Celsius. That means 298 Kelvin. So at room temperature, the hydrogen, helium type of gases will be showing what? Heating effect. Okay, because they're having what? Low values of A. So the low inversion temperature means what now here? Low inversion temperature means that low A value. Okay, that means what? Intermolecular attraction will be less. So we have to say what now here? Less inversion temperature indicates what? Low inversion temperature indicates what? Lesser value of A value. So lesser A value. So lesser A value will be there for the gas of helium and hydrogen. For helium and hydrogen, value of A is lesser. Why? The intermolecular attractions between molecules of hydrogen and between the molecules of helium will be less. When A is less, inversion temperature will be low. Whenever inversion temperature is low for some gases, that gases will be showing what? Only heating effect at room temperature. However, if these gases are just cooled, below inversion temperature and then subjected to Joule-Thomson effect, okay, they will also undergo what? Cooling. Okay, they will undergo cooling, but will not be giving much cooling effect. Slightly cooling effect will be shown by these gases. When we apply what? Joule-Thomson effect, when we subject what here? When we subject the gas to undergo Joule-Thomson effect, after cooling the gases, they will be also showing cooling effect. Okay, but mostly at room temperature, they will be showing what? Heating effect only. They will not show cooling effect at room temperature. So next, if the number of molecules present in 1 cc, okay, if the number of molecules present in 1 centimeter cube, 1 cubic centimeter or 1 ml. And one thing we have to remember here. So here, the inversion temperature, critical temperature, boils temperature. 3 types of temperatures I told now. So the 3 temperatures should not be forgotten. Okay. So what I told you, CBI told now, CBI to remember. TC, TB, TI. So critical temperature, boils temperature, inversion temperature. It is inversion temperature we know. Inversion temperature. And what is this here? Boils temperature. Boils temperature. So it is boils. It is what now here? Critical temperature. Critical temperature. So what is critical temperature now? What we have discussed? Critical temperature is what? The temperature of a real gas. The temperature of a real gas below which only the gas can be liquefied is called what? Critical temperature. So below critical temperature of the real gas only it can be liquefied. And what is boils temperature? TB, the temperature of a real gas at which it behaves as what? Ideal gas. The temperature of a real gas at which the real gas behaves like ideal gas is called what? Boils temperature. And what is inversion temperature of real gas? The temperature of a real gas below which when the gas is expanded suddenly through small hole, it shows what? Cooling effect. And above which the gas shows what? Heating effect. Is called the temperature of the real gas is called inversion temperature. Now what is the formula here? Critical temperature formula is what? Critical temperature. So it is 8 A by 27 RB. And what is TB here? A by RB. And what is inversion temperature? 2A by RB. 2A by RB. So inversion temperature is given by what? 2A by RB. So previously we have taken wrong here. So this should be what now here? So here Ti now here. Ti means what now? 2A by RB. So here inversion temperature and A value. Both are what? Directly proportional. Directly proportional to each other. What we have to understand here, TC means critical temperature is given by 8A by 27 RB, means 8 by 27. 8 by 27 means less than 1. Less than 1 into A by RB. Here it is 1 into A by RB. It is 2 into A by RB. So which magnitude is greater? The inversion temperature has more magnitude than Boyle's temperature greater than critical temperature. Okay. So like this we have to understand. Suppose if a gas is having Boyle's temperature 50 approximately. If a gas is having Boyle's temperature 50 degrees Celsius, what will be inversion temperature? More than 50 or less than 50? Inversion temperature should be more than Boyle's temperature, na? It must be more than 50 value. And if your TB is 50 degrees Celsius, if Boyle's temperature is 50 degrees Celsius for a gas, then critical temperature must be less than 50 degrees Celsius, remember. So the magnitude, the order of magnitude of three types of temperatures is given by, the order is given by TC less than TB less than TI. Is that clear, ma? So whose magnitude is higher here? 2A by RB. So I remember I high, TI higher, TI higher value among the three. Okay. So critical temperature, Boyle's temperature, and inversion temperature. So these three we have to remember. So in all these cases, temperature and A directly proportional. Temperature and A value directly proportional. Is that clear, ma'am? Okay. Now we are discussing what now? Revision point. Okay. What we have learned. What we have learned from this lesson. All the important areas of this lesson we are going to discuss here. So which points here? Important points. Noteworthy points we say. What we say? Noteworthy points of this chapter. If the number of molecules present in 1 ml, 1 cc of a gas, of the gas or vapor, of a gas or of a vapor at STP. Okay, if the number of molecules present in cc of the gas or vapor at STP, okay, that number is called what now? Then that number is called Loschmidt number. Scientist name is what here? Loschmidt. So Loschmidt number is what? The number of molecules present in 1 ml of a gas. In 1 ml of a gas at STP, how many molecules are present? That number is called what now here? Loschmidt number. Okay, so its value is what? 2.687. 2.687 into 10 to the power of 19 per cc, means per ml. Per 1 ml, how many molecules of gases will be there? 2.687 into 10 power 19 molecules will be present in 1 ml. How we got this one, you see? So here we know that 22,400 ml, 22,400 ml at STP, contains what? This much volume of a gas contains what? 6.023 into 10 to the power of 23 molecules. This we know. So these many molecules, I have got a number of molecules. I have got a number of molecules are present in 22,400 ml, right? Then 1 ml. 1 ml means what? 1 cc. Then 1 ml of gas contains how much at STP? At STP, under same conditions of temperature and pressure, how many molecules will be present in 1 ml? So how to get now here? So here 1 into Avogadro number. 1 into Avogadro number by 22,400. So this will be giving what? 22,400. So this will be giving 2.687 into 10 power 19 for 1 molecule, for 1 ml. Okay, next. Now CO2 greater than SO2 greater than SO3 greater than PCl3 is the order of rate of diffusion. Rate of diffusion. Rate of diffusion is inversely proportional to what? Square root of molecular mass. Yeah, M is what now? Gram molecular weight. Okay, ma, gram molecular weight. And already we discussed the rate of diffusion. So if you take first gas and second gas, first gas rate of diffusion, second gas rate of diffusion, R1 by R2 is equal to P1 by P2, P1 by P2, pressure of first gas by pressure of second gas into, okay, under root T1 by T2, T1 by T2. Then M2 by M1, under root M2 by M1, under root M2 by M1. So this relation we have to take it. So R1 by R2 equals to what, ma? R1 by R2 equals to P1 by P2, P1 by P2 into under root T1 M2 by T2 M1. That means what now here? Rate of diffusion is directly proportional to pressure of gas. Rate of diffusion is directly proportional to square root of temperature of gas. Rate of diffusion is inversely proportional to square root of the molecular mass. Square root of the molecular mass. So these three areas very important to remember. So rate of diffusion of a gas is directly proportional to what? Pressure of gas. That's why R1 by R2 equals to P1 by P2. Next, rate of diffusion of a gas is inversely directly proportional to what? Square root of temperature. That's why we wrote R1 by R2 equals to under root T1 by T2. Under root T1 by T2, directly proportional to square root of temperature. And rate of diffusion of a gas is inversely proportional to under root, means under root molecular mass, gram molecular mass. So R is inversely proportional to square root of molecular mass of the gas. That's why we wrote what now here? R1 by R2 is equal to under root M2 by M1. R1 by R2 is equal to under root M2 by M1 we have taken. So this relation is what now here? This is what now? Equation of Graham's law of diffusion. Graham's law of diffusion or Graham's law of effusion. Is that clear? So it's about what now here? Graham's law, important area. Next, so here why we have taken more rate of diffusion for CO2? What is gram molecular weight? Gram molecular weight is equal to what? 44 now. So 44 grams per mole. 44 grams per mole is CO2 molecular weight. So like this, less molecular weight indicates what? Greater rate of diffusion. So here it is 64 grams per mole. Yes, sulfur 32, oxygen 2 atoms, no? 32 plus 32, 64 grams per mole. Like this, lower the gram molecular weight, greater will be rate of diffusion. Is that clear now? So this point you keep in mind. Next, another important point what we have to remember is that vapor density is independent of temperature and has no unit, while absolute density is dependent on temperature and has unit of gram per ml. Gram per ml we take here. Okay, so here vapor density means VD. Vapor density and temperature are independent, means they are not dependent. Vapor density is independent of what? Temperature. Vapor density of a gas is independent of temperature. But absolute density means D. Absolute density means D or rho we take. Rho, otherwise D. So this absolute density, mass by volume is there now. The density will be, absolute density will be dependent on temperature. So when temperature is increasing for the gas, what happens? The volume increases. When volume increases, what happens? When volume increases, density will decrease. So when temperature is increasing, density will be decreasing. So density is inversely proportional to temperature. Understood, ma? When temperature increases, what happens to the volume? Volume increases, na? According to Charles' law, when volume increases, density is given by mass by volume. We know mass by volume. Whenever volume increases, density value should decrease, na? Like that, density will decrease when we increase temperature. So density and temperature, how they are related? Inversely proportional. That's why we write what now here? D1 T1. D1 T1. Okay, D1 T1 or D1 by T1. Generally, we know that what here? If both are direct inversely proportional, if both are density and temperature both are inversely proportional to each other, what we write now here? D1 T1 is equal to D2 T2. Relation between density and temperature. So absolute density means what here? Mass upon volume. The ratio of mass of the gas to the volume of gas is called density, absolute density. So like this, density and temperature both are inversely proportional. But the vapor density is independent of temperature. Vapor density of a particular gas is independent. And also remember what we have to remember, 2 into vapor density. 2 into vapor density of a gas, 2 into vapor density of a gas is equal to gram molecular weight for gas. For the gases, what is relation here? 2 into vapor density is equal to what, ma? Gram molecular weight. If we take CO2, For CO2, what is the gram molecular weight? For CO2, vapor density is equal to what? Gram molecular weight of CO2 by 2. That is 44 by 2. 44 by 2, how much? 22. So 22 is what now? Vapor density. There will be no units. There will be no units for vapor density. No units for vapor density. Just we have to say what now here? Okay. So we have to say what now here? This one. So here for CO2 vapor density is equal to what? Vapor density is equal to gram molecular weight of CO2 44 by 2 will be 22. 22 grams, 22 ml, nothing will be there. No units will be there here. Okay. So like this, vapor density is nothing but half of the gram molecular weight for a given gas. Okay, man. Next, 1 calorie is equal to 4.2 joules. 1 calorie is equal to 4.98. 4.98 means what? 4.2 joules we take here. 1 calorie is bigger unit than 1 joule. Okay, 1 calorie is equal how many joules? 4.2 joules. And 1 kilocalorie is equal to what? How many joules? Into 1000 into. Kilo means how much? 1000 kilo. So 4.2 into 1000, how much? 4200 joules. 4200 joules. Next, the gas which has a least mean free path. The gas which has least mean free path. The gas which has what? Least mean free path. Okay, least mean free path has maximum value of A. A means what now? Intermolecular attractions. A indicates what? Force of attraction. Force of attraction between gas molecules. This A value will be okay, maximum. A value will be maximum if the least mean free path is there. Mean free path means what? When two molecules are colliding, okay, with walls, so the distance between these two, okay, the molecules which are separated by some distance here, how much distance is traveled by the gas molecule before collision? Between two successive collisions, how much distance is traveled by the gas molecule is called mean free path. So if the mean free path is least, then maximum A value will be there. Maximum A value. So mean free path is inversely proportional to what? Inversely proportional to value of A. A is van der Waals parameter. Van der Waals parameter. Magnitude of attractive forces between gas molecules is given by A. So like this, if less mean free path is there, okay, greater A value will be there. When A value is greater, when attractive forces are greater, okay, then what now? The gas is easily liquefied. Which gases will be easily liquefied? If the attractive force between the gas molecules is greater, that means A value, if it is greater, the gas is easily liquefied and has what? Maximum value of Boyle's temperature. What is Boyle's temperature? Boyle's temperature is given by A by RB. A by RB. Now, how A and TB related? The Boyle's temperature is directly proportional to A. Is that clear, ma'am? So if A value is greater, this TB also will be greater. Then maximum A and TB value will be there. So maximum A value, maximum TB value if least mean free path is there. If the gas has least mean free path, maximum A value will be there, maximum TB will be there. And all these values will be more. Why? What is the critical temperature, ma'am? What is critical temperature formula? What is critical temperature formula? Already we wrote now. What is that? Critical temperature is given by the formula. Tell me what is the critical temperature formula? 8 A by 27 RB. What is TB? A by RB. What is TI? 2A by RB. Okay. So like this formula you have to. So in all these cases, A value and temperature directly proportional. When A value is maximum, we have to take what now? Maximum TB, maximum TI, maximum TC. All these will be maximum. Is that clear? Suppose if you take hydrogen gas. Hydrogen gas has what here? Lower value of Lower value of what? A. A is lesser here. When A value is lesser here, what will be greater? What will be greater? When A value is less, automatically these three temperatures should be less, because these three temperatures are directly proportional to A value. When A value is less, automatically all these three temperatures will be less. So lower Tc, lower Tb, lower Ti. All these three will be lower values for hydrogen gas. Okay. Next, when lower values of A there, can be easily liquefied? No, they cannot be. The gases cannot be liquefied. Cannot be easily liquefied. Cannot be easily liquefied. They cannot be easily liquefied. Hydrogen cannot be liquefied. Why? Because of lesser value of what? A. When value of A is lesser, the gas cannot be easily liquefied because the attractive forces will be minimum. When minimum attractive forces are there, the gas cannot be liquefied. Okay. So next, another important point is that for critical constants, what are they? Critical pressure, critical temperature, critical volume. Critical pressure, critical temperature, critical volume. These three are called critical constants or critical parameters. Critical parameters or what? Critical constants. So critical parameters or critical constants are what? PC, VC, and TC. So for critical constants, compression factor Z is less than 1. Compressibility factor is less than 1. So whenever a compressibility factor is less than 1, that will be showing which effect? Negative deviation. Negative deviation. The remaining points we'll discuss in the next class.